Oh, come on, admit it. You like playing with Lego too. These building blocks are pretty fantastic. You can manipulate your object in any way, add these blocks as you see fit, and eventually you may end up with something that looks familiar. 3D printers build objects too, but they can't manipulate the part like we can with our hands. See, most 3D printers that are out there, mine included, it shoots out hot plastic. And as soon as that hot plastic leaves the nozzle, it cools down and it starts to solidify. And if that's all it did, it wouldn't be all that useful because you just have a lump of goopy plastic. So printers have this ability to move the nozzle. And most printers work by moving that nozzle in two directions. So you have an X movement, the nozzle can move X, and it can also move this way, so a Y movement. Some printers have a nozzle that also moves up and down. My printer, the actual surface moves up and down, but the end result is the same. You've basically given your nozzle 3 dimensions of movement in order for it to build the object. Printers, at least my printer, uses this language, or the language that it understands is this thing called G-code. All that G-code is it tells the printer, go here, go there, and while it's going, it can optionally extrude plastic or not. That is essentially it. And so it has this ability to move anywhere in the XY direction, but in the Z direction, it can only move up. So it has to build this object from the ground up, unlike us humans, who can build the object in any way possible. And so that means we have to consider how we prepare the object before we send it to the printer. Consider this letter L. For the 3D printer to start printing it, it needs to start with a solid surface to begin its print on. And then as it moves in the XY direction, it starts to print the first layer. And then it'll move up one notch and print the next layer. And it'll continue doing that until it completes the L. And at the end of the print, you'll have something that resembles an L. Pretty straightforward. What about if we wanted to print this letter T? See, the printer has to start in the same way, start on a solid piece or a solid surface and work its way up. Eventually, it'll get to a place of the T where the printer wants to extrude plastic into thin air. There is no surface for that plastic to sit on. And just like you might expect, the plastic will simply fall down to the ground. So my printer has no way to build this T because of that overhang. So are we stuck? No, not really. We could print this T inverted. If we do it this way, then the bottom of the T, or I guess the top of the T, will have a flat surface for the printer to begin printing on. And then as it continues to print, it will not have any overhangs to deal with. So when the print is complete, we can simply remove our part from the surface, invert it, and we're left with our T. So I mentioned that the plastic that gets extruded from the nozzle is gooey. It comes out hot and it cools rather quickly. But when it does come out hot, it's not liquid. It's a very viscous liquid, so it has a little bit of surface tension. This allows us to be a little brave when we're creating our objects, and we can push the limits of that overhang a little bit so we can get some angles or inverted angles in our print, just like the letter Y. But we can cheat a little bit. If we provide a support on the other end of that overhang, most 3D printers should be able to deal with this. We call this a bridge. Now, as long as that bridge isn't too long, your printer should be able to build objects like this. But there are some limits. Consider the J. This one is a bit tricky. If I wanted to build it from the ground up in this orientation, these angles should be okay to build. But you can kind of see what's going to happen. We're going to get to a point similar to that T where we're dealing with this overhang, and the printer will not be able to print it. Well, what if we invert it and flip it upside down, much like we did with the T? I can start building this side perfectly fine, and the printer will be able to deal with this, but that part right there is going to cause a problem, and most 3D printers will struggle with printing a letter like this J. So an object like this will pose a printer like mine with some challenge. It is unable to print this without doing some trickery. And we have some options. So one of those options would be to separate the print. So print this as one part, and then print this as another part. Remove the parts from the printing surface, and then join them afterwards. Now, how the heck do you join them? There's lots of ways. You can melt the plastic by hand. You can use a screw and screw it in. You can get creative as how you join it, but the fact remains, you will have to figure out a way to join it. Now, whether that's feasible for you depends on the object that you're printing. The other thing we can do is we can use these things called supports. And most 3D printing software, or to be specific, the slicer that you use, has the ability to generate supports, and they'll do it on their own. So if you try to print an object like this and tell your slicer that you're willing to use supports, it will create on its own another 3D printed object like this. And it'll print your J like that. And when you remove it from the print surface, you then have to go and remove the support and end up with your J. And of course, removing your support means that this part might be a little bit messy. You'd have to clean it up. You're also wasting some material. So depends on what you want to do. You might want to use the supports. You might want to use the parts. In all of the 3D printing, I shouldn't say all, because maybe in the future I will change my mind. But for now, the 3D printing that we will be doing, I will not be using supports. I'm going to use the option of splitting up the parts. And you'll find that with a little bit of thought on how to design the object, you actually don't have to split it up all that often. There are some other fancy 3D printers out there that can deal with complex objects like this and not have to put in supports or force you to break the object and put it back together. But mine isn't one of those printers, so I've got to deal with the limitations that I have in front of me. And I know, you're probably thinking, well, I could have just taken the letter and printed it flat. In fact, all of the letters that we went over right now will print perfectly fine when they're flat. But all of these different intricacies that I highlighted with the overhang and the angles and the bridge, all of these are valid things that we need to be mindful of when we're designing our parts, because not every object we print is going to be as simple as a 2D letter. Such as this beautiful thing. We designed this object in FreeCAD. We wrote Python script to create this object line by line. And if you're interested in that sort of thing, I highly recommend you watch the previous video to understand how we built it. I'll make sure it's linked in the description. The reason we built this object is to be an enclosure for the electronics that will go inside this object. This object has a dial on the top of it. In fact, there's another version with buttons. But what this dial does, or the buttons, is it increases or decreases the intensity of LED for our home or business lighting. And so the design of the electronics was done even before the last video. And if you're interested in that, make sure you watch the rest of the journey. I'll also make sure there's a link in the description if you want to see how that stuff was done. Our next step in the journey is to take this digital object and convert it into that G code I was talking about, that 3D printers, or our 3D printer, can understand, so it can create this object in real life. And the thing that creates G code, or it takes a 3D object and turns it into a G code, is known as a slicer. The slicer we're using today is called Cura. It's made by a company that manufactures 3D printers. Unfortunately, the 3D printer that they manufacture isn't the one that I have. Luckily for us, they offer anybody to be able to download this for free and use it on their own printer. Now, in order to get our object into the slicer, I have to go back into the 3D design software and export those parts in file formats that the slicer understands. We designed this model in 3 individual parts. We had the frame, we had the lid, and we had the dial. We also designed an alternative where we used buttons as well. So here's the button for that part and the appropriate lid for that as well. The frame was actually the same frame as the one with the dial. So in FreeCAD, with the part selected, I could go up to export that part and choose a file format that I wanted to export it to. There are lots of file formats in this list, and after doing some comparisons with our slicing software, I figured out which ones we can use. If you're using a different slicing software, then maybe you have some other options here. You'll notice that FreeCAD defaults this file format called step. Now, my version of Cura couldn't import step, so I can't use this. There are some others in here that I can use, and here was one of them, OBJ. There's also a very common format called STL Mesh, and there was also, I think, a relatively newer format called 3MF. Now here's one of those objects imported into our slicer. And I mentioned earlier that this slicer Cura was originally designed for a printer that I don't have. And lucky for us, in the configuration of Cura, I have the ability to choose a non-Ultimaker printer. By clicking on that and taking a look at the list of printers that are available, it's quite extensive. Hopefully yours is in there. And as we can see, mine was. And when I clicked on the machine settings to review all the different configuration, most of this was populated for me, which was fantastic. But I found that I had to adjust the size of my build plate. So my particular printer has a width of 200 millimeters, a height of 200 millimeters, and a depth of 250 millimeters. The other thing I adjusted was the nozzle size. Interestingly, when I installed this, the nozzle size that showed up by default was 0.4 millimeters. My nozzle size is 0.35, so make sure your nozzle size matches what's in the software. The whole purpose of a slicing software is to take this 3D object and transform it into G-code that the printer understands. And it does this by slicing it up into fine layers and then creating all of the motions that the printer nozzle will have to make in sequential order so that we can create this object. And one of the most fundamental settings for a slicer is how thick should it create those layers in the Z direction. And you can see that I've configured the layer height to 0.16 millimeters, and this is very deliberate. I did some research on my printer and found some information about the layer resolution. I discovered that my printer is capable of printing layers as small as 0.05 millimeters each, which is very tiny. And a small layer resolution, remember what that is that is how thick each layer is going to be as it builds this object. So the thinner the layers, the finer the detail that you can create in your object. But there's a downside of this as well. And the downside is the thinner the layers, the longer it will take. So you want generally to pick a layer thickness that is the biggest that you're willing to handle in terms of quality. So trade-off between speed and quality. Through some experimenting, I found that 0.16 millimeters works for me. But why did I choose 0.16 and not something more, I don't know, even like 0.15 or even 0.1 or 0.2? Well, I'm just weird like that. I prefer multiples of base 2 rather than base 10. If you don't understand that, don't worry about it. Just pick something that works for you. Cura organizes the settings in a kind of a neat way. It actually puts it into these little subcategories over here. And if I look at the very first category called quality, that's where I'm going to find the setting for layer height. And you can see I've set it to 0.16. There's also another one here called initial layer height. We'll come back to that. The other setting here is line width. So if the layer height is the thickness of the plastic in the Z direction, the line width is the thickness of the plastic in the XY direction. So in other words, it's the thinnest possible line that our printer can generate as it moves along the surface. But wait. Earlier, we said that the nozzle on my printer has a diameter of 0.35 millimeters. So how can we generate a line that is thicker than the nozzle diameter? Well, remember what we're doing is we're shooting hot plastic out of that nozzle. And when that hot plastic exits that nozzle, it's going to encounter a surface very soon. If this is the first layer, it's going to hit the print surface, the print bed. And if we set our line width to 0.35, in other words, if we match the line width to the diameter of the nozzle, then the printer will push out just enough plastic so that it makes kind of like a square. It'll just literally plop down enough material so that it fits nicely between the edges of that nozzle within the layer thickness that we've defined. So that in our case, that would be 0.35 this way and 0.16 this way. Now, remember, we're dealing with hot plastic, so it's not like you can spit out a perfect rectangle. It's spitting out a gob of plastic. So we want this plastic to bulge a little bit on the sides because the next line that it prints is most likely going to be beside it. And the way that these type of 3D printers work is by fusing that plastic together to make a nice strong print. So we want this bulge to occur. And we do that by telling the printer to push out just a little bit more plastic so that the edges bulge a little bit. We do that, or the way we do that is by increasing the line width in this slicer settings. And I chose 0.4 because as it happens, there is a sweet spot between the line thickness, the minimum line thickness that your nozzle can create and the maximum line thickness your nozzle can create. And it's very dependent on your nozzle. So when I was doing my experiments, I found that 0.4 actually works really well, but it also has another added advantage. It's also a base 2 number. Imagine we wanted to create this solid cube. Our slicer could slice this into layers of which the thickness we've defined, and the 3D printer could just continue to lay down plastic layer after layer after layer, and you'd end up with this cube. It would work, and it would certainly be a cube, but it might be a little wasteful. Really, all we need to make this cube is the exterior walls. Those need to be solid. The bottom and the top need to be solid, and the inside can be filled with less material. And turns out that there is a way to do this so you can retain a structure, make sure that it is still solid, and have a little bit of structural stability while using less material on the inside. The next 3 categories in our Cura slicer include the settings for all of this. So in the walls category, there is a setting for wall thickness, and here it's set for 0.8 millimeters, which given our line width of 0.4 millimeters means that every exterior wall is going to be 2 lines thick. And my experiments for my printer show that to be sufficient. The top and bottom category include a setting for the top and bottom thickness, and in this case it's 0.64 millimeters, which works out to 4 times the layer height of 0.16 millimeters. So that means the bottom is made up of 4 layers and the top is made up of 4 layers. The next category allows us to configure the infill settings. And the infill is the amount of material that goes on inside this cube or whatever part we're making. So you can imagine if we don't include any infill and all we have is those walls, the bottom and the top, then the part that we have won't have a lot of structural stability and I could literally crush it with my hands. That would not be good. So we have to put some material in there, but as we've discussed, it doesn't have to be too much. Well, what's the sweet spot of material and how do we arrange that material inside that gives us a nice strong part without wasting too much material? In my case, I've set the infill density to 10%. So that means that 90% of the volume inside our part is nothing but air. And even with that level of infill, in my experiments, I found that the parts that come out on the printer are actually pretty rigid and solid. So 10% is all we need. Now, depending on the part, you may need more, or you might even be able to get away with less, although frankly, I've never actually tried anything less than 10%. The other thing that's important is choosing an infill pattern. I've picked lines for our infill pattern, but there are quite a lot to choose out of. I would encourage experimenting with these infill patterns. And I don't want to go over them right now because there are tons of content online that describe what these infill patterns are for, or how they look like, what they're good for, all that sort of fun stuff. So feel free, go try stuff and see which ones you like. You may have noticed there's quite a lot of other settings that I'm not really focusing in on, not just in the infill section, but also in the top and bottom, even in the walls up here. Yes, there are loads of settings in your slicer, and these settings allow you to tweak and fine-tune all sorts of things about your printer. We're not going to go into them because it'll take a very long time to do that, and also because many of these settings I just don't understand. They go over my head. And you know what? I consider myself a little bit of a I don't know, an amateur printer. I'm not a professional by any means, but I'm also not a novice. I've played around with this a little bit, and I still don't understand what many of these things do. Yet, I can generate some pretty good quality prints out of my printer. So don't stress over not knowing what all the settings do. If you feel like you have the time to do it, go ahead, enjoy. That's part of what 3D printing is all about is experimentation and figuring out how to get the best quality print. And that's part of the fun of the journey. So if you're up to it, go for it. For now, let's focus in on the essentials. And the next essential is quite important: material. The temperature that 3D printing plastic or filament melts at depends on the type of filament that you're using. There are some that melt as low as 180 degrees Celsius. Some of them require nozzle temperatures up in the realm of like 280 degrees Celsius. So there's quite a big range. And if you try to use a filament that melts at a high temperature but don't give it enough temperature, well, you're going to find that nothing's coming out of your nozzle. And the opposite is also true. If your filament melts at a relatively low temperature and you put it up too high, then your plastic is going to come out all runny and it's just going to make a big giant mess. So you want to make sure that you choose the temperature appropriate for your filament. And lucky for us, when you buy filament on the market, usually that temperature is printed right on the box. So it makes it pretty easy. But you'll find that due to different, humidity conditions and temperature conditions and where you are, you might need to fine tune this. So if you haven't caught on a theme here, experiment. The filament that we're using melts at 220 degrees Celsius, so that's what you see in here. The next category talks about the speed of the print. So going back to the specifications of my printer, I'm able to see the print head travel speed. And according to this document, it says that my printhead can move at a maximum of 200 millimeters per second for best quality printing, but it can travel at up to 450 millimeters per second. But if you look at all my speeds, they're a lot lower. Why? Well, just because your printer's capable of doing it, it doesn't mean that it'll generate the best quality when printing at that speed. I did try printing at 200 millimeters per second, and the quality was less than perfect. So as I slowed down the print, I found that I was getting better quality. So you want to try to find a balance between speed and quality. And the only way you're going to get there is by, well, experimenting. The other thing I've also found is that not every part of the print needs to be printed at the same speed. In fact, you'll get better control if you print different parts at different speeds. For example, so you can see the infill speed here is at 120 millimeters per second, which is still slower than the maximum printing speed or maximum printing capability of my printer. But I found that even at 120, there are some imperfections. So I want to hide those imperfections inside the print. So I don't care if it makes those imperfections because I can't see them. But at 120 millimeters per second, the print is still rigid enough for me to consider good quality. But the walls of the part you do see and do touch. So I've set the speed here at 40 millimeters per second. That is the exterior vertical wall, or all of the walls of the part. And I want them to be excellent. Good quality feel, no gaps, perfect adhesion, all that sort of stuff. So I want to make sure it prints slow enough to get that quality. The same goes for the top and bottom speed. So the top of the part and the bottom of the part are printed at a nice slow 40 millimeters per second. The next one here is the travel speed, and you can see I've set it at a nice blistering 200 millimeters per second, which is actually still a lot slower than the specifications of my printer, which said it can do 450. So why not just put it at 450? It's not printing anything anyways, so who cares how fast it goes? Well, physics gets in the way. See, the print head is comprised of the nozzle, which shoots out the plastic, a heating element to mix or melt that plastic, and it also has an extrusion motor that actually forces the plastic into the nozzle. All of this stuff moves with the head as it moves around to print stuff, which means it has mass and it has inertia. And the faster you move it, I found that my printer actually starts to shake a little bit, especially if I had it up at 450. So in order to prevent the shaking, I dropped down the speed to 200. Now the printer doesn't shake. There's no issues with any parts coming loose or anything like that. And it prints fabulously. And it's still plenty fast enough. So I could speed it up a little bit. I could also play with this thing called acceleration, but I don't really want to get into it because it's complicated, but also I tried playing with it and I actually couldn't get the thing to improve anything anyway. So you know what? Keep it simple, leave the acceleration at default, and just cut the speed into half. It works for me, so I left it alone. The last item in here that's fairly important is the initial layer speed. And you can see that this is set at an absolutely glacial 20 millimeters per second. Now, this is not the first time you've seen this concept of initial thing. So this is the initial speed. You saw earlier about the initial layer height. There's also a few other elements in here or settings in here that control the initial setting of something. And every time we saw this, I said, hang on a minute, we'll come back to it. I'm going to say that one more time. We'll come back to this. The next section here talks about travel. And I don't mean the travel speed. We just covered that in speed. This section here has settings to control the retraction. So remember, we're talking about plastic that's being extruded out of a nozzle. Now consider the printer has made a line. So it's been extruding plastic and then it gets to a point where it needs to stop, move to another location, and then begin extruding again. Well, in that move, there is no extrusion happening because that's what the instructions were given to the printer. However, because we're dealing with goopy plastic, there's a chance that during the move, some of the plastic may drip out and leave a little bit of a strip or a goop or even a blob. So this idea of retraction says before you move, suck that plastic back in the nozzle to prevent any from dripping out, and then resume extruding by the time you get to your new location. So this retraction has been, for me, extremely helpful. So I've enabled it in these settings. The next section is cooling. Now I haven't really messed around with these settings too much because the default works for me. Remember, the reason we need cooling is because the plastic that's coming out of the nozzle is coming out at a very hot temperature. In our case, it's coming out at 220 degrees Celsius. Then as soon as it leaves the nozzle, it has to solidify and adhere to anything that it touches. So in order for it to solidify, it has to cool down relatively quickly. So most 3D printers, mine included, has a fan mounted directly at the nozzle, or it's aimed directly at the nozzle, so to help it cool down as fast as possible. So the settings in here basically say that yes, we want that fan to be running, we need this thing to cool down, and the fan is going to be running at 100% speed at all the time, except for the initial layer. There's that initial layer setting again, which, yeah, you guessed it, we'll come back to that. Next, we have support, and we've talked about this already. You remember the idea of printing a letter like the J, and we need something to hold that piece up as a support, and we decided we're not going to print those for our models, so that's why you don't see a checkbox there. And finally, all those times you heard me say we'll come back to it, now we can get to it. Build plate adhesion. All of those initial layer settings, they matter quite a lot. See, the very first layer that comes out of your printer nozzle is going to hit or get attached to the print bed. Now, the print bed on my printer is made of glass. Your printer may use different things, but the way that the very first layer sticks to that print bed is extremely important, because when that first layer sticks, the next layer is going to be added by the printer, and it needs to match perfectly. It has to line up with the previous layer. And the next layer has to line up with that layer as well, as you might imagine. Now this printhead is zipping back and forth, doing its stuff. What if it accidentally catches on the top layer of the print? If the bottom layer has not adhered very well, the printer might just knock it right off the print bed, and you've had a failed print. Worst of all, your printer won't even know that it knocked it off, and you're going to get all sorts of spaghetti. And for some printers like mine, the nozzle actually only moves in an X direction. The Y direction is handled by the print bed, which actually moves back and forth. And if it moves fast enough and that bottom layer is not adhered strongly enough, well, yeah, that might happen. Well, in my case, it looks like the first layer was adhered pretty strong. If the first layer isn't actually stuck on well, the whole print will actually get knocked off in that scenario. And this concept of print bed adhesion is a pretty big one. I mean, just Google it and you'll find loads of people having problems with their print adhering to the bed really well. And these settings for the initial layer are there to help resolve that. Back up in the quality category, you can set an initial layer height thicker than the layer height. And the reason we do that is for the nozzle to push out more plastic onto that print bed so it sticks better. The material category has an initial printing temperature to heat up the plastic a little bit more to stick better to the bed. The speed category has an initial layer speed because if you print slower, then the adhesion of that layer to the previous layer is going to be stronger. And since this is the first layer adhering to the bed, we want that to be extra strong. So we print extra slow. And the cooling category has an option to turn the fan off for the initial layer, which is great. Let's get that nice goopy plastic to stick to the bed as best we can. And if you're still having problems getting the first layer to stick properly, the settings in build plate adhesion may be able to help. You could create a skirt. All the skirt really is it's a piece, or I guess it's a layer of plastic that gets extruded before your actual print does. It's not attached to the print in any way, but what it does is it primes the nozzle. So if there's any gunk left in the nozzle, it'll push it out and make sure that the plastic that's being used for the actual model is of a better quality, thereby the first layer being stuck to the print bed very well. I use a skirt a lot because I like to purge the model purge the print head before we start printing the model. Another option I've used is brim. And with brim, you increase the size of the first layer, basically the surface area. So you're creating a very large surface area, or I guess a larger surface area, to attach to the print bed, which should improve adhesion. It works really well. The downside though is when you actually remove the print from the bed, you have to remove the brim from the print as well. And sometimes you get a little bit of a rough edge, which, nobody really likes. The final option is raft, which I've actually never used, but it creates a few layers of, I guess, a buffer between the print head and your actual model. Can't comment on it since I've never tried it. The next option here is for dual extrusion, basically two print heads moving at the same time. My printer's not capable of that, never tried it, so I'm gonna have to skip it. As I will with mesh fixes, special modes, and experimental. I'm sure there are tons of tiny little knobs and dials that you can tweak in there to your heart's content if you wanted to experiment with the print. We're not gonna go there. Enough talk, let's slice. The first object we're gonna slice is the button. There it is. I've imported it after exporting it from FreeCAD, and now we just hit this to get the thing to slice. Done. And then we go up to preview and take a look and see what the printer is going to do. There's a nice little slider on the right which allows me to go through all of the different layers or slices of this model. There's also a slider on the bottom which shows me how the printer will generate the part. I think this is so cool. Let's zoom in a little bit. As I slide the slider, you can actually see a fake outline of the print nozzle as it creates or extrudes all the plastic and starts building the object. By the way, the piece that it's creating now is the skirt around the object. Notice how the next piece of the object that it starts printing is completely disconnected from the skirt. It's also a different color. And if I show the key over here, you can see that the helpers, which in this case is a skirt, is that nice cyan color. We have the inner wall, which is the green, and then we also have the shell of the print, which is red. Now, of course, the actual printer is not printing in those colors. It only prints in the color of the filament that I've installed in the printer. These colors are just here for us to visualize what's happening. If I continue sliding the slider, it will continue to go and print all of the different pieces of that very first layer. And when we're done, we can see the first layer of our model on the print bed. As we start moving up the layers, we can see how the printer is sequentially creating these layers in order. And then we get to a point where we start to have a problem. Right there. Layer 39. So let me back this up and you'll see what the problem is. You can probably already tell the problem, but if you weren't clear about it, after it gets to layer 39, which by the way is now see how we've created the I guess the stalk of the button, and it's going to start to create the pushing part of that button. And there's the nozzle where it's going to start, and it's going to start extruding material. Now, you may notice that that first ring that it extruded is extruded in midair. Yep, it's similar to that T problem we faced. And if we actually tried to print it this way, we're just going to get a big mess of spaghetti on the printer. It will not do very well at trying to print this model like this. So what do we do? Well, with the T, our solution was to invert it. Let's try it. I'm sure there's an easier way to do this, but with Cura, I can take that object and kind of virtually manipulate it. So there, I'm going to flip it around 180 degrees and then click on Arrange All Models so it's exactly where I want it to be and lock it. So now that model is sitting inverted on the print bed. And let's go ahead and slice it. Click the preview and let's watch and see how this thing prints. It's going to start with the skirt, work its way in, and then it's going to start building up its layers. That orange stuff is the infill. Remember, we set it to 10%, so that's why there's some quite large gaps in between there, but it's okay. It's on the inside of the button. We're never going to see it. The printer will continue to create its layers as it creates the rest of the button. That will work. Let's try slicing the dial. Hit slice, click preview, and let's take a closer look. Starting from the beginning, print the skirt, print some of the inner bits, and print the first layer, and we'll move up. And there's the infill, and oh, here is our first problem. Gotta back it up a little bit. By the time it reaches layer 26, the first thing that comes out of the printer is an inner wall on the exterior of this dial. The next thing it does is our problem. It wants to print a circle, yep, in midair. So again, this is not going to work. It's not going to print in this current orientation, so yeah, you guessed it. Let's flip this one upside down and see how it works. Okay, let's back this up to the beginning and watch the print. There's the skirt. And the inside, this is now the top of the dial. Whoops. And we'll keep adding layers as we go. There's the infill. Oh, and look at this. You can see how the dial is actually angling out as it goes up from the bottom. There's that angle we talked about. That angle is similar to our letter Y. And in this case, we can deal with it just fine. Let me zoom in as tight as I can get onto these angles, and you'll see the individual layers that our slicer is creating. And it's only overhanging those layers a little bit off the last one. So the printer should be able to print this until we get to that moment where there it is. That's the moment where it failed on the correct orientation print. But you can see in this situation, it won't really have a problem at all. It will just print on top of that existing infill and continue the print as normal. This one will also print just fine. Here's the lid of our enclosure, which I'm just about to slice and preview. Starting the print, we can see, as always, it starts with the skirts and then starts printing the model. And right away, I can tell that this is going to be problematic. I mean, look at the shadow here. The shadow is quite large, which says the model is going to cover a lot of the, or the part is going to cover a lot of the build plate. But the first layer, I'm done with the first layer. And the first layer includes only those two little things. So it can't quite balance on those two little pieces of plastic. And of course, we're going to run into that same problem of printing in midair again, aren't we? And sure enough, there it is on layer 5. If I back this up, we can see that the printer wants to create that outline. And yep, that outline, it's hard to see on this because it's only 5 layers up. I mean, it's still less than a millimeter off the bed, but that little gap is enough to make this print fail. So once again, we're going to flip this one on its end. That looks much better. And as we start building layers, we can see this model come together. Now, there are some very interesting things about this model that I want to point out, and one of them happens right about here. Okay, so at layer 17, let's back this up a little bit. All right, so pay special attention to these hex pockets over here. These hex pockets are places where we're going to insert metal hex nuts to serve as screw anchors. There is no material in there. And when I start the preview, we can see how the printer is going to start creating all sorts of material around it. And then this is not the important part. The important part starts right about here. All right, let's zoom in. You can see what's happening here. So remember, there is no, that's inside that hex pocket, that's empty space. So the printer is going to print a little circle around it. And then it's going to, well, okay, another circle. And then it's going to start okay, a third circle. Goodness sakes, man, just get to it. There we go. It's printing material across that gap. But if you look carefully, on every end of those lines, there is some supporting material underneath. The printer has very cleverly created its own bridge so that it's able to make that pattern. The bridge is similar to the H example we did at the beginning of the video. As long as you have two supporting elements and this bridge isn't too long, you will be able to do that. That's exactly what's happening here. And then it proceeds to do one for the other hex pocket on the other side. Why did we create a bridge? Well, let me continue the build and we'll explain what's happening. So I'm going to go up another 2 layers, and then at layer, well, okay, maybe 3 layers. At layer 21, let me back this up a little bit. I'll explain it. So if we zoom back into where those hex pockets were, see how they're covered up. You can't see them because they've been covered by material. And the printer will continue to create, right there. So it's creating a circle on that platform. This is where the screw is going to go into to anchor into that hex nut behind that material. It'll become apparent as I keep going. So let me build more material onto this. And you can see how the printer will continue to print. And there it is. It's becoming really apparent now. You can now clearly see a hole inside that area. But that hole is separated from that hex nut by that extra bit of material. And that was done in order to support this internal circle. The slicer did not come up with that. This was designed into the model when we created it in the previous video. And that's why I'm stressing this a little bit here, because this is an example of a scenario where we cannot print if we don't use any extra supports. This is a J example for us. So in order to accommodate that, I needed to consider this in the design. Now that we slipped that little extra bit of material in there, our printer can print this successfully. And then once it's done, I can then take this part over to my workbench and use a real drill and finish off that hole. And finally, let's slice the enclosure. This one prints actually really well, but I did have to make some of those modifications that you saw earlier. So let's zoom right over there. So if I go to layer 6, I'm trying to get there, 69, and I back that up, we can see how these holes right over here where the print head is right now, it's going to cover that up with that artificial layer. So it is able to create that circle, which is going to serve as a screw shaft. So that same thing we saw on the lid is happening here as well. There's also some other neat examples of bridging. If I go to these hex pockets, which are actually being created on the side, and I back this up a little bit, you can see how, well, this isn't actually bridging. This is the same as that angle I was referring to earlier, the Y. So here's the sides of those, or I guess the top corners of that hex pocket being printed with slight overhangs, but not too much that it upsets the balance. And if we turn it this way, we'll also see an example of the same thing, I guess, but it's doing it for this hole on the side of the enclosure. And that last little bit there, there's the bridge that covers off or caps off that hole. Once we're happy with the preview, we can just click this button to save it to disk, which saves the G code into a file that we can see. Let's take a look at it. This is the language that my 3D printer understands. And there's a bunch of lines that begin with a semicolon, which usually means a comment, so the printer will just ignore anything after a semicolon on that line. Those are usually here for us humans to understand what's happening. But there are some codes here, M82, G21, M140, blah, 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 blah. Luckily, there's some comments that tell us what that code actually means. So a bunch of configuration and preparatory codes to turn on fans and turn on heating stuff and doing all sorts of business. And then we get into the real nitty gritty. So this one, there's a comment here that says this is layer 0. So this is where we're going to start off and look at all these commands. Almost all of them begin with the G1. So a G1 is a command that tells the printhead to move to a location. That's really all it is. So you can see the X and the Y. So we're not changing the Z here. We're just changing our X and Y position. And the E stands for extrusion. So that's how much material the printer has to extrude while it's moving. If I scroll down a bit, you may find, oh, I think I saw it. There it is. There are some G0 commands as well. And the G0 command is a move without extruding. See, it does not have any E to it. It does, however, have an F, which I think stands for speed. I'll have to double check that. But that's essentially it. This code or this file is comprised of mostly G1s, and there are a lot of lines. I'm going to go right to the end. Look at this. We're at, it's over 218,000 lines to create this. That's a lot of G code. Here's an online resource that describes what the G code actually does. And the first item in this list, of course, is this G0, G1, linear move. Adds a straight line movement to the planner. So just like I said, a G0 or a G1 moves from here to there in a straight line, and it either doesn't extrude or it extrudes respectively. Now you may notice the second line here says a G2 or G3, arc or circle move. So G code does have the ability to create arcs and circles, but I don't think I saw any in our code. Let's take a closer look. Bringing back our G code, if I do a quick search for G0, I should find a whole bunch of them. And sure enough, I do. You can see me clicking through the G0s here. I'm going to do a G1 search, and as expected, a whole lot of G1s in this document. Let's do a search for G2. Nothing. I can't find a G2 in the entire file. And I'd expect the same for a G3. Yep, no G3 in the entire file. But wait a minute. We have some curves in our object. We have some decreasing radius cylinders here. We have an exterior curve over here. So why didn't we find any G2s or G3s in the code? Well, I did some research into this, and it turns out that most slicers don't actually use the G2 or G3 functions of G code. So you can take a curve and approximate that curve with really small straight lines. And if you make those lines tiny enough, then you won't even notice that it's made up of straight lines, and it would appear like a curve. And it turns out that most of these slicers do just that. They approximate a curve using a series of short straight lines, which also explains why there's so much or so many lines of code in that G code file, because a lot of that is dealing with those curves. Speaking of curves, there's a little bit of a tangent that I'd like to take us on to. And I want to bring this up because I feel kind of bad. See, in the last video, there was a step that needed some explanation, but I very conveniently skipped over that explanation, and it left some people confused. So thanks to KNR5045 that brought it to my attention in the comments that there's this whole bit that seemed like magic, and it just happened without any explanation. And it has to do with how we generated those curved edges around the enclosure. So let me cover that a little bit right now. In the previous video, we were creating this part in FreeCAD using Python code. And there was a stage where we had the part with sharp edges like this, and through some code changes, we were able to make the edges rounded like this. And unfortunately, there was a step that I just skipped over in the explanation. Here is part of the code that generates this box with the sharp corners. And the line that I want to focus in on is this line right here, line 92, where we call this custom class constructor called bbox. Basically, this class constructor takes in 2 points or vectors. It takes in the opposite corners of where we want this box to be, and it goes and generates that box. And then without adequate explanation, in the next phase of design, I added in a third parameter, which takes in a vector that describes the curvature that I want on those corners. But what I forgot to do is explain how this third parameter is accepted into the class constructor. So if I go back to the square corner version and open up the class constructor of bbox, we can clearly see that it brings in 2 vectors. This is one of those corners, and here's the other corner. Switching to the upgraded class connector, we can see that it now has this additional parameter. This is the thing I forgot to show in the last video. This parameter accepts a list of joints, which we don't actually do a whole lot with in this class constructor. However, we do send it off to the B-flat class constructor, which actually does do something with it. And if I open up the B-flat class constructor, there's the list of joints that it does accept. What the B-flat class does with that list of joints was adequately described in the previous video. It's just that I skipped over the part where you can also pass that parameter into bbox and have bbox send that to B-flat. Now, I appreciate that if you didn't watch the previous video, what I just said is a bunch of gobbledygook. And that's okay. If you're interested or you want to find out more about what's actually going on here, go take a look at the previous video. Like I said, it's linked in the description. But if, Python coding really isn't your cup of tea, well, it's probably not going to be that interesting for you. So just skip it and we'll move on. Now that our slicer has generated the G-code file, I could send it directly to the printer and let it do its thing. Oh, look at the time it's going to take to do this one. I love the smell of a fresh 3D print. By the way, I would suggest to not do that if you're using a filament that has toxins in it. The plastic filament that we're using here is PLA+, which is supposed to be biodegradable and friendly for the environment. So I feel comfortable doing that. But there are plenty of filaments out there that do have toxins in them. So if you're using some of those filaments, please follow the recommended ventilation guidelines for your printer and don't inhale this stuff, because I hear some of them are pretty nasty. But check it out. Here's the inside of that print. Printed really nice. Some nice detail inside. You can see the ventilation holes. Here's the lid that's supposed to fit on top. And of course, the dial, which fits, well, around the dial. And here's what you haven't seen in this video, but this is the part that we've been creating in previous videos, and it's supposed to fit nicely inside this enclosure. So if I do this right and align it properly, ooh, that went in with a very satisfying snap. I could then take our lid, position it above, another satisfying snap, take our dial, align it. It's not screwed in yet, so it's going to fall apart if I let it go, but oh, that is very nice. So now that we've created the enclosure for the electronics, the next bit is to create the other end of this system and the light that's supposed to be lit up. Now, if you've been watching the previous videos, we've already created the electronics. We just have to make an enclosure for that light, wire it up to this, and see how the thing works. So join me next time.